Hello guys, how's it going? Can you hear me? Let me see if I can see myself.
No way.
Okay. So, I guess everything must... Oh, let me make the sounds has issues again. Okay, now you must be able to hear me well. Is everything okay? How was the contest for you? It was a very hard contest. I see, yes, today it's contest. Sound has any issue? Or it's okay? Okay. So yes, today was div 1 plus div 2, so it was harder than usual, definitely. I think I have solution for problems A to E, and we will discuss these problems. We will discuss all the problems from A to E, and I think if you're okay, we can start now. Shall we start discussing problem A? Okay, let's go. Awesome. Let's go. Okay, let's talk about problem A first. Let me just make sure everything is right. Okay. So, problem A, distanced coloring. It says that you received an n by m grid from a mysterious source. The source also gave you a magic positive integer constant k. And it just says that if you want to color all the cells, just if cell x1, y1 and x2, y2 have the same color, there are two distinct cells with the same color, maximum of x1 minus x2 and y1 minus y2 must be greater than or equal to k. You don't like using too many colors, find the minimum number of colors needed to color the grids. Okay, so it's easier than usually. What? This contest was easier. Okay, so what it is saying? It says that if x1, y1 and x2, y2 have the same color, maximum of x1 minus absolute value of x1 minus x2 and y1 minus y2 must be at least k. Okay, what does it mean? Well, it basically means that if you have some color in a cell, like for example, this cell is blue, for example, it's like you can consider that there's an imaginary rectangle surrounding it. There's an imaginary rectangle like this around it, such that the distance, let me draw this in the middle. This is not our main rectangle, this is just an imaginary rectangle that we consider that is surrounding our cell. So in order to show that this is just an imaginary rectangle, let me show it like this. And no cell in this area can have same color, can have color blue as well. So no cell in this area can have the same color. It's like that we have an imaginary rectangle around this point and the distance to each side of it is k, and no other cell can have the same color in it. So basically, let's assume that n and m are both greater than or equal to k. If we consider a k by k at the top left of this grid, let's consider a k by, so these are n and m, and they are both greater than or equal to. They are both greater than or equal to k. So basically we can say that it is like n by m. It is like we have a rectangle of, we can consider a k by k in the top left, and we can say that all of these cells must have different colors. Okay, all of these cells must have different colors. So we're gonna need at least k squared colors. We need at least k squared colors. But at the same time, we can say that k squared colors are enough. Why? Because if we color this k by k squared, we can just keep repeating the same pattern in the whole string. For example, this is color 1, this is color 2, 2, this is color k, this is color k plus 1, 2, color 2k, and this is color k minus 1 times k plus 1, 2, color k squared. Then we can keep repeating the same pattern. Again, here put 1, here put 2, here put 3, and so on. So the point is that we can have blocks of k by k, and we can keep repeating this pattern. And this way, we're gonna need exactly k squared colors. This is the case that n and m are at least k. So if n and m are at least k, we know that we need at least k squared colors, and at the same time, k squared colors is enough. Therefore, the answer is gonna be k squared in this case. Is it clear? Please, if it is clear for you, use, so far, I haven't completed it. If so far it is clear, please use this emoji or put a plus in the chats. Okay, no problem. I explain again if it is not clear. So what I'm saying is that if n and m, the sides are both greater than or equal to k, I'm gonna need at least k squared colors, because if you consider the top left k by k square, in this part no two cells can have the same color. No two cells can have the same color in these parts. So we're gonna need k squared different colors for these parts. But at the same time, k squared colors is gonna be enough, because we can just keep repeating this square, the pattern of this square. And maybe in here, just a part of this pattern will be repeated. So we can just consider each cell, we can consider x modulo. I mean, if we consider some cell I and j, we can consider that what is I modulo k and what is j modulo k. And based on this, we can define the color. So it's like we have several k squared blocks, and in each of them the same pattern will be repeated. Therefore, k squared colors is going to be enough. Okay, I hope that it is now clear. Now I say that assume n and m, one of them, for example, is less than k. For example, n is less than k. Well, the point is n is less than k. We cannot have a k by k squared in the top left. N is less than k. We cannot have a k by k squared, but we can consider a k by n. So it's like if n and m are less than k, we have less rows and less columns. So we do not need to consider those additional rows and columns. And therefore, in this case, in each of the directions, if n is greater than or equal to k, we can consider the first k rows. If n is less than k, we just consider the first n rows. So we only consider the minimum of n and k rows here. And about m as well, we consider minimum of m and k. If m is greater than k, it is going to be k. If m is less than k, it's going to be m. If you consider this block, in this block, every two cells must have different colors, and this pattern will be kept repeated. We can keep repeat this pattern in the rest of the, if there's anything like, for example, if n is less than k, in the rows there's nothing left. So we can just horizontally repeat this pattern. We can keep repeating this pattern, and this way at the end we will have all the cells colored, and these colors have that difference that we want. Is it now clear? If this problem A is completely clear, please again use this emoji, this one, or put a plus in the chats, or if you need further explanation, tell me. Yes, exactly. So the answer is just minimum of n and k and times minimum of m and k. Awesome. So yes, so the answer, let me write it in here as well. The answer therefore is gonna be minimum of n and k times minimum of m and k. This is gonna be our final answer. Awesome. I see. Okay, so shall we move on to the second problem? What's your salary, you're asking me? Or someone else? So, let's move on to problem B. Well, my salary, I'm working on a lot of things. Right now I'm a PhD student here. I'm working in a startup. I'm a developer in a startup. So, not bad, but we can talk about it later. So, let's move on to the second problem. Removals game. It says that Alice got a permutation A1, A2 to AN of 1 to N, and Bob got another permutation B1, B2 to Bn of 1 to N. They are going to play a game with these arrays. In each term, the following events happen in order. Alice chooses either the first or the last element of her array and removes it from the array, and Bob also does the same. And the game continues for n-1 turns, after which both arrays will have exactly one remaining element, x in the array y, A and y in the array B. If x is equal to y, Bob wins, otherwise Alice wins. Find who will win if both players play optimally. Okay, in this problem, I can say, let's consider, so we have these two permutations, P and Q. Assume that, I want to say a fact. Let me write it like this. We have a fact. I want to tell you a fact. If there exists two elements like x and y, such that they are adjacent in P, but they're not adjacent such that they are adjacent in P, but they are not adjacent in Q, but not in Q. Alice wins. Alice can fool Bob, and Bob cannot win. Alice wins in this situation. So let me explain to you what I mean exactly. What I mean is this. So by this fact, I mean that assume that this is your P, and this is P, which is for Alice, and this is Q, that is for Bob. I'm saying that assume that we have two elements like x and y, such that in here x and y in P are adjacent, but in Q x and y are not adjacent. In this situation, I'm saying that Alice will definitely win. Why? Her strategy can be like this. She can just keep removing all the elements except x and y. So in her first n minus 2 moves, she will remove all these elements in any order that she wants. So she first can remove this prefix and then this suffix. So now n minus 2 elements are removed. Okay, n minus 2 elements are removed now. Now what Bob can do? Bob cannot save both x and y. Bob cannot save both of them because they're not adjacent. Bob must also remove n minus 2 elements, but those 2 elements that remain from the beginning, they were adjacent, because you cannot remove something from the middle. You can each time remove something from the beginning or from the end. So you cannot remove something from the middle of the permutation. Therefore, those last 2 elements that will remain for Bob are going to be adjacent as well, but they cannot be both x and y. Both x and y cannot be saved by Bob, so at least one of them is lost. In the best case scenario, Bob can save one of them, not both of them. For example, assume that Bob cannot save both x and y. So one of them will be lost, one will be lost, and without loss of generality, assume that y is lost. Okay, without loss of generality, assume that y is lost. Okay, so what we can say is that in this case, Alice can now remove x and can be sure that Bob cannot have x, cannot have y anymore. So Bob cannot make the 2 numbers equal. So Alice's strategy is like this. If Alice can find 2 numbers, x and y, that are adjacent in P, but they're not adjacent in Q, Alice can save these 2 elements after n minus 2 moves. Remove everything but these 2 elements. But Bob cannot save the exact 2 elements. So at least one of them is lost. Without loss of generality, assume that Bob has lost y. Bob does not have y anymore. Alice can remove x now and have y, and because Bob does not have y, Alice will win the game. So in this case, so this fact is proved, and in this case, definitely Alice wins. Is it clear so far? If it is clear, please use this emoji again or put a plus. Awesome. No, I'm just assuming that there exists some x and y that are adjacent in P, but they are not adjacent in Q. I'm not talking anything about x and y's that are adjacent in both. I'm not considering them. So assume that, for example, 2 and 5 are adjacent in P, but not adjacent in Q. Alice will remove everything other than 2 and 5 and does not consider any other elements. And then she can just save those 2. Bob will lose one of them. For example, Bob will lose 2, so we can keep 2, and for sure Bob wins. I lost the track that there are so many messages. Is there a solution for normal and not specifically a permutation? I think if the set of the elements are not the same, if the set of the elements are the same, it's gonna look like permutation. But especially if you have duplicated elements, I think it can be a bit more complicated. But I think that is solvable as well. I think it seems solvable that way. Okay, so, okay, awesome. So now, this is the first case, but what is the second case? What if no such? What if no such x and y exist? what if no such x and y exists? We know that if such x and y exists, Alice wins. But what if no such x and y exists? The point is that this is a very special situation where either p is equal to q or p is equal to reverse of q. Why? Because consider p1. Consider p1, the first element in the first permutation. Because the set of adjacent elements are the same, p1 in q must come either first or last. Because in here p1 has two, we know that two elements have one adjacent and n minus 2 elements have two adjacents. Those n minus 2 elements that have two adjacent elements, in here also they must preserve those two adjacent elements, so they must be in the middle as well. So p1, when p1 has one adjacent element in here, also in here it should have one adjacent element, so it should either come first or last. If it comes first, the rest of the array, if q1 is equal to p1, the rest of the array will be uniquely determined, because in here again p2 must come, so q2 is equal to p2, in here again p3 must come, and so on. And in this case p is gonna be equal to q. And in the other case, where p1 comes last, again this one must be p2, this one must be p3, and so on. This way q is gonna be reverse of p. And so this is just these two cases. It's a bit better, there's no difference, but it's a bit better if I write q is equal to reverse of p, not p is equal to reverse of q. They mean the same thing, but I think this way of writing is better, because p is our base and we're writing q based on p. Q is either equal to p or equal to reverse of p. Okay, I argue that in this case Bob wins. Why? Because in the case where p is equal to q, in both cases, let's not make it case by case. In both cases, whatever Alice removes, Bob can remove the same thing. Whatever is first or last here, in here it is also first or last. So either first or last. So if, for example, if q is reverse of p, if Alice removes the first one, Bob removes the last one. If they have the same order, if Alice removes the first one, Bob also removes the first one. So whatever Alice removes, Bob can remove the same thing. So at the end, when one element remains, that element is the same in both of them. So the point is that if no such x and y exist, we can say that q is equal to p, or q is equal to reverse of p, and in this case Bob can easily win with a very simple strategy. Look at what Alice has removed, remove the same thing. Okay, so now is this case also clear? Let me get back to chats. If you are clear, if it is clear for you, please again use this emoji or put a plus in the chats. If it is not in the chats, you can tell me to explain it again. The point is that either such x and y exist that they are adjacent in p and they're not adjacent in q. In that case, Alice wins, because Alice can keep these two elements and Bob cannot keep both of them. And in the last move, Alice can keep the one that Bob does not have it anymore. But if no such one exists, no such pair exists, Bob can just repeat everything Alice does, and at the end they're gonna have the same number. Will the approach change if Bob was to move first? If Bob was to move first, it would be, I think, always Alice wins. Why? Okay, let's answer this question. If Bob moves first, just imagine that in this problem it was said that Bob is moving first. If Bob was moving first, Bob initially removes one of the elements. For example, removes x. Alice can remove everything but x. Then Alice is sure that x is not left for Bob, So Alice can remove everything but X in the next n-1 moves. So if Bob moves first, because Alice sees what Bob is doing, Alice can win for sure. Because Bob is removing something and Alice can keep the same thing. Okay, shall we move on to problem C now? Okay. I think, I'm sorry that if I'm missing some of the messages, there are a lot of messages at the moment. But I try to, and if you had any other questions, let me know. And guys, for further discussion, you can always join our Telegram channel. I again invite you, you're more than welcome to join our Telegram channel, and in there we can do further discussion. Whenever I find time, I try to answer all the questions there. And also guys, if you like the live stream and you want to support the work, you can like the video or subscribe to the channel, no pressure, but if you wanted to support this work, you can do this. So let's move on to the third problem. It says that there are n circles on a two-dimensional plane. The ith circle is centered at x, y, and y, y. Initially, all circles have a radius of 0. And the circle's radius will be increased by a rate of 1 unit per second. You are currently at xs and ys. Your goal is to reach xt and yt without touching the circumference of any circle, including the moment you reach xt and yt. You can move in any direction you want, however your speed is limited to 1 unit per second. Please determine whether it is possible to do this. So you are at points x, s, and ys initially, and you want to go to points x, t, and yt. And there are several circles in here that each time the radius will be increased by 1. First, I prefer if I change the way that I'm looking to the problem a little bit. I mean, these radiuses, etc., and these circles that we have can be looked at in another way. We can look at it like all it is saying is that whenever you go to a point, all it is saying is that whenever you go to a point, the distance from xs and x sub s and y sub s to that point should be strictly less than the distances of this point to any of these points, to these additional points. Okay, so if the distance from xs and ys is t, we can be here at time t. If the distance of this point from xs and ys is t, in the best case scenario, we can come here at time t. And it means that the distances of all these centers from this point must be greater than t, so that these circles do not reach here. So basically what it is saying is that to any points that you go, you need to make sure that the distance from xs, from your source, from x sub s and y sub s to that point is gonna be less than the distances of these centers from that point. Okay, so this way we can get rid of circles. It's like for any vertex, we have some value that if we want to be there, we should be there by at most this time. If for these each points, we just consider this minimum distance to these centers, this gives us a value that tells us that if we want to be here, we must be here at most by this point, by this time. Okay, this is a better way of looking at this problem, and you'll see why. So now, if I look at it like this, I can easily first say a fact. Again, what is my fact? I'm saying that if the minimum distance of our destination xt and yt of xt if the minimum distance of xt and yt to one of the centers is less than its distance, less than or equal to, is less than or equal to its distance to xs and ys, there's no way. X sub s and y sub s, there is no way to get there. So what I mean is that if you consider your destination xt and yt, this is a point in here. If its distance to one of these centers of those circles that the problem is mentioning, if its distance to one of them is less than the distance of xs and ys to this point, then there's no way that we can reach there. Because if this distance is, for example, t, we can be in here at time t in the best case scenario. But at the time t, this circle reaches there sooner than that, because its radius is also increasing. So there's no way that we can do it. Okay, so I'm saying that if the distance of x sub s and y sub s to x sub t and y sub t is greater than or equal to the distance of this destination to one of the circles, then there's no way that we can get there. Okay, is it clear so far? So far, is it clear? You can again use the emojis or put a plus if it is, otherwise let me. Means circles are like rectangles? No, they are not rectangles. They're like circles. I mean, each time at time t, they can reach all the points that their distance is at most t from this vertex. So at time t, they can reach all the points that their distance to this point is at most t. So the point is, if the distance of one of these centers, to this destination is less than or equal to the distance from this source to this destination, then there's no way that we can get there, because this circle gets there sooner than we do. So in this case, the answer is definitely no. This is our first fact. Otherwise, I say that otherwise, the answer is yes. Otherwise, the answer is yes. Why? I say that otherwise the answer is yes, because if you consider the shortest path from xs to ys, if you consider this shortest path from x sub s and y sub s to x sub t and y sub t, if you consider this shortest path, I'm saying that if we just go through this shortest path, none of these circles will threaten us. None of them can have any effect on us, because if any of these centers can touch any of these points when we are there, it means that the distance from this circle to that point was less than or equal to the distance of us to that point. And if that happens, then the total distance of this vertex to our destination is also less than or equal to the total distance of our source to our destination. So if this happens, because then we're gonna have a path like this to our destination, and this path in total is gonna also be less than or equal to this path, because this part was less than or equal to this part, and this part is the same, is constant, is the same for both of them. So if for any of the points on this path, this additional point can get there sooner than our source gets there, or less than or equal to when our source gets there, they can get to our destination as well sooner than or equal to when we get there. So this is gonna be case number 1. But in here we said that we don't have this case. We are sure that the distance from our source to this destination is strictly less than any distances of any of those centers to the destination. Okay. So this way I show that in otherwise it is, the answer is yes. So all I'm saying is that in this problem you should consider the distances. And what are the distances? Distances between 2 points A and B, and A1, let's say A1 B1 and A2 B2, A sub 2 B sub 2. The distance is gonna be A1 minus A2 squared plus B1 minus B2 squared under the square root. But when you want to compare, you can just forget about this square root, because we just want to compare these numbers. We want to see that which one is smaller than the other one. So you can just do not take a square root. If their square root is less, the square root of some number is less than the square root of the other one, itself must be also less than the other one. So you can just keep these parts so that you don't get involved with doubles, etc. And you compare these values. If for the source it was minimum, for the source it was minimum, the answer is yes. Otherwise the answer is no. If for the source it is strictly less than all the other ones. Okay. Is it clear? Please again use the emojis or put a plus, and if it is not, let me know. Let's say it is 0. Why do we need to do any binary search? What if speed was variable? That would be a bit more complicated. I think if it was, the point is that in that way, it's like we also have a coefficient that this distance. Yes, I think this works. Yes. Yes, I think the speeds, if the speeds are variable, it can work. That's, you just multiply these distances by 1 over their speed, or divide it by their speed. I think that will also work, because if they're gonna meet each other at some point, they can also meet each other at the final points. So I think that must work. And guys, one more thing that I need to mention, maybe you get confused that when we are calculating distances, we just consider straight lines. But in here, what I said is that we can have this path, which is less than this path. But it is okay, if any non-straight path exists, at least one straight path also exists, that its distance is at least as good as what we had. So I mean that when such a path exists to roots which is less than or equal to this path, the straight path is even better. So if this is at least as good at that, the straight path is also at least as good at that as well. So therefore it is okay that if we consider the passes that are not straight, they are not the best passes. So if it is okay if we consider them, because if they are better than something, the best possible path, which is the straight path, is also better than that. Okay. How to handle floating points precision? As I said, in this specific problem, the best way to handle it is to not using floats and doubles. I'm saying that get rid of this square root. Just consider this squared. So let's define this squared, I showed with these two, as xt minus the x of the point we are considering squared plus xt yt minus y sub t minus y sub I is the point we're considering squared. So this is our this squared, and just consider this squared. Just compare them. Do not find out what the distance itself actually is. Okay, this way it's gonna be easier for you. You do not need to handle the float precision, etc. Yes, exactly. If the circle can reach the endpoint earlier than the player, then the circle will also be able... No. Vice versa. If the circle can reach any points on the path sooner than the player, that circle can also reach the final destination sooner than the player. Why? Because if, for example, the circle can reach here sooner than the player does, this is in the shortest path of the player. So if we consider this part and add this part to it, this is a path from the circle to the final points. But this is the path of the player to the final points. This is gonna be less than or equal to that, which means that the circle reaches the endpoint sooner than the player does, which is bad. Okay, so I hope that it is now clear for you. Shall we move on to problem D? Thank you very much. Shall we move on to problem D now? Yeah. Yes. Right. Okay. Nice. Let's move on to problem D1 now. From here it's getting a bit more complicated. I'll tell you about the solutions that I have in mind. Let's see what's gonna happen. So the first problem, the first part of problem D, problem D1, DFS checker, easy version of it. In this problem, you have a binary tree and you have a permutation of all the vertices. You have a permutation of all the vertices of this binary tree, and you need to answer Q queries. For each query, you are given two integers, x and y. You need to swap p sub x and p sub y and determine if p1 to pn is a valid DFS order of the given tree. Okay, and the swaps are persistent. They will remain, after doing them, they will remain in the next queries. Everything will not be reset. So, and the DFS order is like this. I mean, you run a DFS, the order of the vertices you visit. I believe that you already know this. And it is not unique. You have to say that. So after each swap, you need to say if this is gonna be a valid, if the order that we have is a valid DFS order. So what I can say in the first case, in the first part of the problem, that we have a binary tree and our limits are also up to around 10 to the 5th. So what we can say in this problem is that for each of the nodes, we know that this node has a specific height, and this height shows that, for example, this height shows that what is the size of its subtree, because we have a perfect binary tree. Okay, we have a perfect binary tree. What is a perfect binary tree? A perfect binary tree is like this. I mean, it means that each vertex except leaves has exactly 2 children and all the leaves are at the same height. All the vertices except the leaves have exactly 2 children and all the leaves are at the same height. So it's something like this. And this pattern can be extended. Again, these vertices can have 2 children and so on. So I'm saying that based on the height of each vertex, it's easy to find out that what is the size of their subtree. And it's easy to say that what is the size of the this vertex itself, the size of the subtree of this vertex itself, what is the size of its left child, the subtree of its left child, and what is the size of the subtree of its right child. So for example, if there are L heights here, L levels here in this subtree, it means that the number of vertices is gonna be 2 to the power of L minus 1 if there are L levels of vertices. And in each of the subtrees, there are exactly 2 to the power of L minus 1 vertices. Okay, and L, if this vertex is not a root, L is more than 1. We have more than one level of vertices. So anyway, all I'm saying is that in the subtree of each vertex, we can easily find out that how many vertices exist there based on their heights. Based on their heights, we can find out the number of levels in their subtree, and we can find out how many vertices exist there. So what we can say is this. We can say that for any vertex in here, for any vertex that we have in here, it has, if it is not a leaf, if it is a leaf, it is good. It can be anywhere. So if it is a leaf, it is good and it can be anywhere, that's fine. But if it is not a leaf, it has exactly 2 children. Okay? It has exactly 2 children. One of the children must be exactly next to it. And as long as we know this L, based on the level, we know this L. One of the children must be exactly next to it, and the other child must be exactly after 2 to the power of L minus 1 vertices. So we know the position of their children, the 2 children. We know that where exactly these 2 children must exist, right? We know that where these 2 children must exist. And we can just, this vertex is okay if and only if these vertices are really its children. So if for a vertex you know the value L for it, the only thing that you need to check for this vertex, the only thing that this vertex must have is that the next vertex of it in the array, and the vertex that is after 2 to the power of L minus 1 vertices. So its distance is exactly 2 to the power of L. These 2 vertices must be its children. And if for all the non-leaves vertices these holds, then we can be sure that if for all the non-leaf vertices it holds, we can say that this DFS order is a correct DFS order. Because you see that all the children will be seen in the correct, in the correct order. First you see this child, and this recursively in here everything is gonna be okay, because again for this vertex its children are these 2 vertices, and again for them this will be repeated, and so on. So everything will be nice, and we have a correct DFS order. Is it clear so far? Is it clear so far? Again, if it is, you can use this 100 emoji or put a plus. If it is not, tell me to explain it again. So I'm saying that for the first part, it's just enough to say that for any of these vertices, the one next to it and the one that is 2 to the power of L after it must be its children. If it is, we say that this vertex is okay, this cell is okay in this case. In this case, we can say that this vertex is, this cell is okay, and we will check it, and we need to just make sure that all of the vertices are going to be okay. So, and this is something that we need to make sure for all the vertices that are not leaves. So, when I swap 2 elements, which elements can be changed? When I swap 2 elements, assume that I have some px and some py, right? I have 2 elements, px and py, and I want to make sure, I want to see that after we swap these 2, if everything is gonna be okay or not. Well, for which of the cells things will change? For which of the cells thing will change? Definitely two of the vertices that I should see if everything is okay for them again is px and py themselves, because their position is changing. The elements in these two cells is changing. So I need to again check if their children are okay. Also, I need to check their parents. Maybe their parents were counting on them. I mean, they were in a correct position for their parents, and now that they are moving, their parent is losing them. So the point is that one is themselves, that I need to consider them again, and also is that maybe their parents are counting on them. What do I mean? I mean that they were in the correct position for their parents, and now that they're moving, their parents will lose them and they're not okay anymore. So first I just do this swap in two steps. First, I will remove the elements from their current positions. First, I remove them from their current positions, and then I will insert them into their new position. So first of all, I will remove these elements from their current position, and then I will insert them back again into their new position. So how can I do this? How can I remove them and insert them back again? First, about the removing part. First, I know that if this point was okay, now it's not okay anymore because it's being removed. If this one was okay, it's not okay anymore, so it is removed. And about the cells about their parents, I know that what is the level of these vertices. So assume that I am removing a vertex from here. Assume that I'm removing a vertex from here. So I know that where its parent must be. If I consider L for it, I know that its parents has 2 to the power of L plus 1. I mean, L for its parents is 1 more than this one. So its parents has exactly 2 to the power of L plus 1 minus 1 elements. Okay. So, and I know that each of its children has 2 to the power of L minus 1 elements. So where the position of its parent must be, if the parent is counting on this vertex, the parent must be either here, or it must be exactly be at distance 2 to the power of L from it. Okay, in here the distance was 2 to the power of L minus 1. In here is L minus 1, not L, when I'm considering this vertex with its children. But in here, when I'm considering this vertex with its parents, its distance must be 2 to the power of L. So the parent must be either next to it and 2 to the power of L from it. So I can check both of the positions and I see if the parent of them is there. If it is, it means that their parent is counting on them. So I need to make sure that, okay, I need to tell the parent that, okay, you're losing this child. So I need to change the variable for that parent. Okay. So this is how I can remove these two elements. This way I can make sure that these elements, their own value will be removed because they are not okay anymore. A vertex was here, but there is no vertex here anymore. So this vertex itself is not okay anymore. And also their parents might not be okay anymore as well. So I can have I can consider 2 cells for their parent, and if their parent is in one of these 2 cells, tell them that, okay, you lost one of your children. For example, they can have a count at how many of their children do they have in the right place right now. I need to decrease that value by 1 because they lost this child. And now how do I insert these 2 vertices into their correct position back again? What I can do is to insert these vertices back again into their positions is that when I put it in here, again, first I can see that what is the value for itself, how many of its own children are in the correct place. I know that I need to consider again 2 positions, 2 fixed positions. One of them is the one next to it, One of them is the one that its distance is 2 to the power of L minus 1, 2 to the power of L minus 1 to it. If I can see that how many of these are really the children of this vertex and update the counter of this vertex this way. And also, again, I need to see if their parents have earned a new child. If now they are in the correct position for their parent, again, I need to check the vertex 1 before it and the vertex 2 to the power of L before it. And if their parent is in one of those positions, I will increase their counter by 1. And the point is that the counter of all the vertices must be equal to the number of their children. That is the only way that my DFS order is really a correct DFS order. And how can I check that? Each time that I'm updating CNT of a vertex, I can check that if this CNT is equal to really the degree of this vertex. And by degree, I mean the number of children. The parent is not considered in degree in this definition. If it was equal and it is not equal anymore, I have a global num as well that says that how many of these vertices are correct. Some people maybe think like they need to use segment tree or something like that to solve this problem, but that is not needed. You can just keep several values. For example, you can keep a counter for each vertex, that's how many of their children are in the correct position, and have a num that says that for how many vertices the CNT of V is equal to deg of V. And the point is that if CNT of V was equal to deg of V for some vertex and now you're decreasing CNT, right after that you need to say num minus minus. If CNT of V was not equal and now you're increasing and now it's becoming equal, right after that you need to say num plus plus. And the only thing that you need to check is this. You will see out if num was equal to n, yes, otherwise no. And this is gonna be your answer. If I want to be more precise, I should put an endel in the end, at the end as well, but let's keep it short. Is it clear? Let me know if it is clear completely. So this is the solution that I had in mind for this problem. I hope that it makes sense for you. Please use this emoji or put a plus in the chat if it is okay for you. And wait a minute, this light is off in here again and it bothers me. Let me for a second turn this light on. Sorry for that. Okay, sorry. Now you see that it is on. Okay, shall we move on to problem D2? Well, the point is that if we solve D2, we don't even need this solution anymore because D2 is the general form of this. Now we solve for the specific case of having a perfect binary tree. But in general case, if you solve it, then everything is solved and we do not really need this specific solution anymore. Okay. So if everything is okay, let's move on to problem E2 now. D2 now. Problem D2, DFS checker, hard version. This is the same problem, only now n is up to 3 times 10 to the 5th, q is again up to 10 to the 5th. Previously it was 5 times 10 to the 4th, but now it's 10 to the 5th. And also it is a general tree, it's a generic tree. It can be of any form. So the tree is given to you, the parents are given to you. It's not necessarily a perfect binary tree anymore. So what I had in mind for this part, for D2, was something like this. I was thinking about having some data structure like segments, and the point is that when you put a vertex at a position, you know the size of, for example, assume that you put v in here. You know the size of subtree of vertex v. You know that what is the size of subtree of vertex v, and assume that you have also calculated the starting times and finishing times of v. I hope that you know what are starting times and finishing times of v. If not, that's completely okay. I think maybe it's better if you skip this problem for now, and this problem might be a little bit soon for you to be approached. But how many of you know what is starting time and finishing time? If you don't know, I think you can. For now, it's better if you skip this problem because it might be a bit soon for you to solve such a problem, and that's completely okay. So, in short, let me tell you this: starting time. I will give you a short introduction, but again, I'm telling you that if you don't know it already, maybe it's not the best time to solve this problem. But in short, start time and finishing time says that let's assume that you have a tree. Let's consider one random ordering of it. I mean, run a DFS on one random ordering of it, and let's have a timer, and each time you increase this timer, and just keep track of when you entered each vertex and when you exited each vertex. For example, first assume that we come to this vertex at time 0. Then we increase timer, we come to this vertex at time 1. Then we come to this vertex at time 2. We exit this vertex also at time 2. Then we enter this vertex at time 3. So when we enter, we will increase our timer. But when we exit, normally, when we exit, we do not increase timer. But in some problems, we can change that. And as you see in this problem, we will change that as well. So we will enter this vertex at time 3. We will exit this vertex at time 3. We will exit this vertex at time 3. And then we will enter this vertex at time 4. Enter this vertex at time 5. Exit this vertex at time 5. Enter this vertex at time 6, enter this one at time 7, exits at time 7, enter at time x, enter at time 8, exit at time 8, exit at time 8, enter at time 9, exit at time 9, and you see how it's going. So you just keep track of when you entered and when you exited each vertex. These red values are starting times when you entered a vertex. Those green values are finishing times when we exit. It was better if the colors were swapped, but anyway. So yes, it's similar to that. So this is gonna be like this, starting and finishing time. But again, I just wanted to give you a short introduction of what it is. But it's better if you're more familiar with it if you want to solve this problem. And what I was thinking on this problem was this: if you keep starting times and finishing times of the vertices, when you have a vertex in here, a vertex v in here, it imposes some rule about the vertices in here from v to in this period of size of v. Size of v is the subtree of vertex, size of the subtree of vertex v. It talks about this interval and it imposes a rule about this interval. It says that the starting times of all the values in here must be at least this much and at most this much. For example, they are at least st of v and at most ft of v. And let me tell you that using a starting time and finishing time, u is in the subtree of v if and only if starting time of u is between starting time of v and finishing time of v, inclusive, exclusive. And also size of v is always equal to finishing time of v minus starting time of v, with this definition of a starting time and finishing time. But I want to change it a little bit. I want to change the values of a start time and finishing time a little bit. I want to also say that let's increase the timer when you want to calculate finishing time as well. So for example, in here, when we want to exit this vertex, again, our timer will be increased by 1, and we exit this one at time 3. And then in here, a starting time will be 4, finishing time will be 5. So let's assume that we will also increase our timer when we want to exit. Why do I do this? This way, our timer at the end will be 2n instead of n. I do this because in this problem, I'm more comfortable if all the starting times and finishing times are unique. I mean, this is just a tiny change, very tiny change. It doesn't matter much. So I'm just saying that when you want to exit a vertex, also in that situation, also increase the timer. Because I'm just more comfortable if all the values are unique in this specific problem. So yeah, I want all of them to be distinct. So now I know that all these values are distinct. So this u, I mean, it says that in all the vertices in here, if it is a correct DFS order for each v, if I check that in the interval of this vertex v, if all the vertices are in the correct interval of starting time to finishing time, then this vertex is okay. This vertex is checked and it's okay. And then if all the vertices were checked, all of them are correct, then I believe that my answer is correct. I mean, this is a correct DFS order. So what do? I just say that each one of these vertices impose a rule on an interval. Let's use segment tree, and in each node of segment tree, just have 2 sets. And in these 2 sets, just keep that. What are the, we know that the rules imposed are a form of some L and R. It says that all the starting times in here must be at least L, and all the starting times in here must be at most R. All of them must be in this interval. So let's have 2 sets and store all the lower bounds that we have. Have 2 sets, one for all the lower bounds that we have and one for all the upper bounds that we have. And each time we just need to make sure that all the numbers are greater than or equal to even the greatest lower bounds, and they are less than or equal to even the lowest upper bounds. Okay, so now I keep all the conditions, all the lower bounds and upper bounds in a set, and this way I can easily add a new condition to all those segment nodes. And I can also at the same time remove conditions from those nodes. And also I can have a set to keep all the starting times and finishing times as well. I can also have a set to keep all the starting times and finishing times of that node. And what I'm saying is that when you remove a vertex from some point, again, I do swaps in 2 parts. First, I remove those vertices from their positions, and then I insert them in their new positions. So when I remove a vertex, if I do both remove and insert, if I do both, what are you storing in a node? I'm just storing 3 sets. All the lower bounds imposed on that node, all the lower bounds, all the upper bounds, and the values, the starting times of the vertices in that node. So I'm saying that when you remove some vertex, first of all, you need to remove its rule from this interval. That's easy. It's an operational segment. You will remove them from the lower bounds and upper bounds. And this is where that uniqueness of values helps. You can easily erase those values. And so the rules will be removed. And also, this vertex value will also be removed from all the nodes. And the insertion is exactly opposite of that. A new rule will be added to some nodes, and also the value of this vertex will be added to several nodes. And then all the nodes that are involved, I need to check them again to see if they are okay now or not. Maybe they were previously okay and they are not okay now anymore, and maybe they were previously not okay and now they are okay. So I need to consider all the involved nodes and check them back again to see if they are okay now. And I can easily do that because when I do updates, several nodes will be involved. Several nodes, their situation will be changed. So I can easily just check them back again and I'll see that if now they are okay or not. And this way I can just have a value, for example, like that says that like how many of my nodes are okay, and then or how many are not okay. And if at least one of them is not okay, the answer is no. But if all of them, if the counter of not okay nodes is 0, then the answer is yes. All the nodes are okay, and the answer is gonna be yes. And this way, this was the idea that I had to solve this problem. Is it clear? Again, if it is clear, please use the emoji or put a plus in the chats. Is it clear now? So this is my idea. So maybe someone has a better solution, but this is what came to my mind after thinking about this problem. Got the idea, but not very clear. So the idea, yeah, but the idea is just keep all the starting times, finishing times, and then have a structure, a data structure of segment tree, and then you have several rules that must be imposed on several intervals. You can break your interval into several intervals, segment intervals, and impose that rule on all of them. In each one of them, you keep all the lower bounds and all the upper bounds, and you also store all the values. When you erase a number, you should just remove all those rules and remove the value of this vertex from all the nodes that have this vertex. And when you insert the rule at somewhere, you should do vice versa. You should add a rule and also add add the value to all the nodes that have this vertex. So that's going to be the whole idea. And you need to have again a counter that how many nodes are okay. And if you implement this, D1 will be handled as well. Has any of you in the stream solved D2? Has anyone solved it with the exact same solution? Yes, coding it is hard, and if it is above your level, that is completely okay. I mean, you need to spend a lot of time, solve a lot of problems. It's better if you first focus on problems that are currently at your level, and over time your level will go higher and higher, and you can solve harder problems. So that completely makes sense. That's completely okay. Yeah, D2 is gonna be hard to implement with this solution, and maybe all of the solutions are also hard. Okay, vector set and parent array to check. Okay, so yeah, there definitely exists several other solutions for this problem as well. Okay, nice. Do you have any further questions about D2, or shall we move on to problem E now? Problem E is the last problem that I've read, and I have solutions for it. So if you want, we can now discuss that one. And guys, again, if you like the video and you want to support my work, you can show that with liking this video or subscribing to the channel. And also for further discussions, if you want, you can join our Telegram channel at this link. Okay, the upper bound, lower bound thing that I was discussing was this. I'm saying that each of these nodes, for each of my segment nodes, I keep two sets. The sets of all the lower bounds and the sets of all the upper bounds. Because there are several nodes that they impose some rules on this segment node. Each one of them give us some upper bound and some lower bound. Each one of them give us some lower bound and some upper bound. So I store all of them in two sets. And when I want to insert, I will insert those two new rules, those two new values in this node. When I want to remove it, I just erase than from my notes. And that's gonna be all. Yes, the code will be complicated. Yeah, that is right. That is right. I believe that the code of this problem was not easy. And let me see that how many people accepted it in the contest. As I see, around 1,000 people have accepted it in the contest. And I see the solutions. For example, let me share my screen. For example, when I see, for example, Jiang Li's solution, who won the first rank, it's very long. Let's see Radebush's solution. It's also long, relatively. So yes, it seems like all the solutions are relatively long on this problem. And it's not very easy to be implemented. Best resources to learn CP. I discussed these things in the live streams. But for now, maybe you can start watching the guidelines videos in the channel. I have talked about such things before a little bit, but guys, each Friday from 12 to 14 GMT, we have a stream, and would love to see you there. We have live streams Fridays from 12 to 14 GMT each week. We'd love to see you there if you want it. So, yes, if your code is short, yeah, you can send the link here. And yeah, I will try to cover all these guideline questions later on. But for now, maybe it's better if we continue talking about the contest, because I believe that a lot of people are waiting for the problems to be discussed. So, okay, but let's say note the starting is on the left of the segment and the ending is in between the segments. Then what will the set? Still, you know, you're using a segment tree, right? When you are using a segment tree, you have several nodes in all of them. I mean, you break your interval into several segment nodes, and in each one of them you will insert your lower bound and upper bound. So each one of them, on each one of these nodes, your rules will be imposed. So that's what segment tree handles for you. Okay, if I understood your question correctly, this is what your segment tree handles for you. Okay, so you have an interval, it will break into several segment nodes. In each one of them, you will add these lower bounds and upper bounds. Okay. Okay. So let me talk about problem E then as well, if you have no questions left from problem D, and if you had, you can say this. Any idea about the rating for 5 key range? Not sure about it. Yeah. But the ratings will be, if you're talking about the ratings, they will be released soon, hopefully. So you will see it very soon. So problem E, given an array of integers S1, S2 to SL, every second cosmic rays will cause Si such that I is equal to 1 or Si is not equal to S of I minus 1 to be deleted simultaneously. And the remaining parts will be concatenated together in order to form the new array S1, S2 to S of L prime. You define the strength of an array as the number of seconds it takes to become empty, and you are given an array in a compressed way. You have several pairs A sub I, B sub I, such that it represents A sub I copies of B sub I. So your array is the concatenation of all this. And you need to say that for each I from 1 to n, you need to find the strength of the sequence described by the first I pairs. So you have this array in the compressed order. You have this array in the compressed order. So you have several blocks. All the blocks in the compressed way, they are given to you. In all of the blocks contain several of the same value, several elements of the same value, and you need to see that what is the strength. Again, on this problem, that the idea that I had, the idea that came to my mind was this. You can, I think you first you will add pairs one by one. So assume that so far you have solved the problem for these pairs, and now a new pair will be added. So you solved it for the first I pairs. Now you want to solve it for the first I plus 1 pairs. No, I will not solve H. I just raise problems A to E, and I only solve them. In infinite time we can solve it by reading the statements right now, but because it takes a lot of time, I think it's better if we skip them for now. I hope they will be covered in the text editor. They will for sure will be covered in the text editorials. So when a new pair will be added, a new block will be added, what we can say is that what I want to do is to keep all the blocks, that when a block will be added to the end of my blocks, it is possible for it to be matched with one of them. So I mean that, for example, assume my sequence is currently this. For example, it's 2, 1, 3, 2, 2, 2, 3, 1, 1. You know, if you have this, what I say is that what are the blocks that maybe in future an element can be merged with them. I mean by merging, I mean that, for example, assume that you have several x's here and a y in here and several x's in here as well. When you remove this y, we know that each time from each block its first element will be removed. So next time the first element of each block will be removed. So this y will be removed, these x's will be removed as well, the first x's. And then these two parts will be merged with each other. These two parts will be merged with each other after that. So what I'm saying is that if you consider all the blocks, that is possible that later on, if an element will be added here, it is somehow possible that it will be merged with one of these values. I can say that this block is one of the candidates. This block is not, it is never possible that anything can be merged with these three. But this block is also a candidate, because you see that if you have a 2, you have several 2's in here. First time this 3 and this 1 and this 2 will be removed, and the next time again this 1 and this 2 will be removed, and these 2 are removed, and then these 2 can be merged with this one. So I'm saying that I'm keeping all the intervals, all the blocks that can be somehow merged later on with something. So this block can be merged by, it is possible, it is a candidate to be merged by the future blocks. But this one is not, this one is not anything. We do nothing can be merged with this one in the future. This one is not, and this one is not. So for these ones, it is never possible. It is never possible to be merged. Yeah, I read the problem. I also thought about segment tree a little bit, but that didn't work. And then I started thinking about this. And the point is that we can keep all these blocks like this in a stack. We can keep a stack, and in this stack store all the blocks that is possible for them to be matched with something in the future. Okay, so in a stack we will keep them all. We will keep all the elements that is possible for them to be matched with something in the future. And the point is that, and the one that is last, the one that comes last in the stack also comes on top. So The point is that when you have already several blocks and several of them are in the stack, for example, these are in the stack, assume that a new block will be added. I can start from the end. For example, these are the blocks in this stack. So I'm right now just considering my stack. This is not my array. This is my stack. So what I do is I start, for example, this is x and it has a number. I have some n of x, for example, here. Each time I can compare it with the last block, and I will see if it can remove the last block. I will see that which one of these two will remain longer than the other one. So I will see that which one of these two blocks will survive more than the other one. And it's easy to see that. I should just see that how many elements are here, how many elements are here. If the number of elements in here was greater than or equal to, is strictly greater than the number of elements in here, this one survives more. Okay, if this one has more elements, this one survives more, so it won't be removed from our stack. It won't be removed from our stack. We just also push x to the stack as well, because x is also something that can be merged in the future. X is the last one, nothing is removing it. So always x can be merged. Maybe even the next blocks are several x's. For example, we have a 1 here, we have some 1 here, and then again several x's. These x's might be able to be matched with this x. So this x will be pushed in the stack and we're done. But if n sub x was at least as good at this value, this value is less than or equal to, if this value, let's call it y with y and n of y. We have y and n sub y in here. If n sub y was less than or equal to n sub x, the point is that from now on, nothing can be merged with this one. Because as long as this block survives as well, and it disconnects these new elements from this block. So as long as this survives as well, and it disconnects all the elements from these two sides. So I can say that in this way I can erase this one from our stack. I can pop it from our stack. And also from nx, let's just keep some variable like car. Initial car is nx, the number of x's in this block. I will subtract car by n sub y. Because I want to see that, okay, now after the deletion of this block, how many of these x's are left. And then again, I will compare car. So car is the thing that I will compare each time. I see that right now how many x's I have. Again, after that, when this one is removed, this block will be next to this block. And I know that right now it will have car elements. Again, I see if car was less than this value, I just do not erase it from stack and I will just push x. But if car was more than that, this one will also be removed and car again will be subtracted by n of z, for example. This is a block of z and it has n sub z elements. So car will be subtracted by n sub z. And I will continue doing this, and if at some point I reached a block such that I again saw x, so I reached some block with the same value. If I reached a block with the same value, these two blocks now can be merged. So all I do, for example, if this is x with some value like s, for example, what I will do is to just remove this block, because this block will be considered here now. I will again remove this block because it will be merged with this block, and I will set the value of this block as car plus s. Because all the remaining elements in here will be matched with these s elements in here. So I just remove this, and when I want to push this new block of x, I push car plus s. So I should just consider that if at some point I reached the same value, I reached a block with the same value, I need to just merge these two, because now from now on these two blocks are meshed. And their value is going to be car plus s. And this way I can have my stack. And the point is that all of these values that I have in my stack, all of these blocks are the blocks that can remain and be matched with something in here. And you can see that these newer values in my stack are weaker. They cannot remove the previous ones. So I have some older but stronger blocks that remain longer, and some newer and weaker blocks. They will not survive a lot, but because they're new, they can easily be matched with the new blocks. So I have some older and stronger ones and newer and weaker ones. And the point is that the first block in here will be removed the last, because it will last longer than anything else. So this one is the stronger and remains the most. And I think I can say that it's just enough to see that how long this oldest one will remain. And that's not easy, that's not hard to say. It is, I mean, the its answer is gonna be its second. I mean, as I said, if there was no merge, if I had no merges, I just push x and nx here. If there were no merges, I can just, for each block, let me say it like this. Instead, let me say it like this. I can just say for each block when it will be deleted completely. I can just see that when it will be deleted completely. If it will be merged with something, the point is that it's like some additional values. Some car will be added to this one. So if it was previously s, now it becomes s plus car. Because car new elements of x are added to it. But if it will not be merged with anything, it's just pair of x and nx. Because it has nx elements and it exactly will continue to survive for n sub x steps. So if you consider this second value of these pairs, they are the time that it takes for these values to survive. And it's like when we compare these two elements, we see that which one survives more. And if this new one survives more than this older one, it means that this older one is weaker than this new one. And it also comes before this one, so it can never be merged with a new block. So I will remove it from a stack. So this way I can easily find out that how many steps it takes for the strongest block to be removed. And this way I can say that how long does it take for me for all the elements to be removed. This is my solution for this problem. I hope that it is clear for you. Did you understand it? Do you have any questions about it? If you have any questions, feel free to say that. Otherwise, again, you can use this emoji or say put a plus in the chats. Okay, awesome, nice. Nice. Okay, great. So I think that was all about the stream today. We solved problems from A to E, and the next contest is gonna be in 2 days. There's a Div 3 contest in 2 days. I'm gonna see you there, and do not forget to attend our Friday streams. I would love to see as many of you as possible there. This way I feel that it is more helpful for people. And if you wanted to watch the previous ones, you can always do that in this playlist. In this playlist you can watch all the topic streams that we've had so far, and we just have had 2. We just have had 2 so far, and this week we're gonna have the 3rd one. We're gonna have a poll in our Telegram channel to see that what is gonna be the topic of the next one, and we will decide this with your votes. We decide that's what is gonna be the topics of the next time. Also, it's time Fridays from 12 to 14 GMT was decided in the Telegram channel. So if you want, feel free to join the Telegram channel. The link is pinned in the messages. And again, guys, if you wanted, you can like the video and subscribe to the channel. I think that would help my work. If you wanted, you can do this. So one suggestion: it will be easier to clear doubts if we all connect to Discord or some voice channel. You mean that we talk with voice instead of messages? I mean, we do it with voice and video in the live streams, but some parts might remain, and maybe we can just. I mean, voice is okay. Yes, you're right. Voice is very important. Voice and video is very important, but that's why we have the live streams. But about the additional ones, maybe we can check in different times, etc. Maybe we can use text, but yeah, whenever we want to use voice, I think we can use Telegram, YouTube live streams and talk in person, exactly. But if you believe that, I don't know if if YouTube has a feature so that the audience can also use voice or not. I will search for that. Maybe I will add that as well. If it's, I think that would be nice. Thank you for the suggestion. I think that would be nice if we can just add the feature of audience talking. I see. Yeah. Yeah, but I want to somehow maybe integrate it with the live streams. If in the middle of live streams, maybe someone can talk, etc., that would be nice. TLE bots? If you mean TLE bots, we have TLE bots. You know, we have this Discord server as well. Our Discord server is, there are a lot of members in our Discord server as well. And we have TLE bots there. So yes, thank you a lot for your suggestions. I will think about it and try to add. And guys, I really love your suggestions. And I believe that it helps me a lot to increase the quality of the live streams, and it can make it more beneficial for you. So feel free to give me your suggestions. I think they are extremely helpful. You can suggest in the comments below, or in here in the chats of the live streams, or in the Telegram, or in Codeforces, or in Discord. Whenever you want it, give me your suggestions, and I will try to read all of them, and I will try to apply them in the live streams. I think that helps a lot, and I would really love to hear your suggestions to improve our work. Okay, the light is finally gone as well. Let me. Okay, now it's better. Okay. And you can see my thoughts on the wall as well. Okay. Nice. Thank you, Abhishek. I will especially disclose that my writing is counterfeiting that film. That's okay. You need to solve a lot of problems. Just source code. I mean, that happens a lot. If you see anyone's plots, you see these patterns that at some time they just keep falling down. That's completely okay. That's part of it. I mean, you can't expect that always you will grow, or you know, it has some randomness and some variance. That's completely okay. So just keep practicing, and by practicing I mostly mean sorting problems in Codeforces, especially around with difficulty around your rating, and try to accept them. I think that helps you a lot. Okay, and guys, thank you a lot for joining today. I hope to see you again in the live stream in 2 days on Div 3 contest and also in the topic streams. Also, if you want, I can see you in the social media like Telegram and Discord as well. So, see you next time, guys. Thank you a lot. Bye-bye.